Well, welcome to Chapter 7 Light. This is Unit 4, and here we'll talk about the particle theory of light. So, we've talked about the wave characteristics of light, and we looked at certain experiments that demonstrated that the light, as we know it, and other electromagnetic waves have wave like properties. So, where does the particle like behavior come in? We talked about light having energy and this energy being transferred to other materials, and that happens when light interacts with different materials. Typically, when light energy is absorbed, there's an increase in temperature. For example, if you stand outside on a sunny day, you feel warm in the sunlight, and that's because of the increase in temperature from that transfer of energy. So, absorbed light can also have other effects. So let's look at an experiment that was done to show some of the effects of this absorbed light. And this was an experiment that was done by Albert Einstein. So in these cases, when the energy from the light is absorbed, we talked about the fact that when energy is absorbed, that the electrons in the atoms jump to high energy levels within the atom. And in some of those cases, the movement of the electron due to energy that the electron has acquired from the light is called the photoelectric effect. And so we have light coming in, like we have in this image, the light coming in, hitting a surface and actually giving the electrons enough energy to be ejected from that surface. And that's what's the photoelectric effect. So according to the wave theory, more intense wave will have greater energy, and therefore the ejected electrons should have more energy. But that wasn't really what was so. It wasn't the greater intensity, because when this experiment was performed, it didn't matter how bright the light was. There was another factor that affected the energy that these waves had. The kinetic energy of the electrons was seen to depend more on the frequency of the waves and not the intensity of the waves. When we first started talking about electromagnetic radiation or electromagnetic waves, and we saw that spectrum, we talked about the higher frequency waves like the X-rays and gamma rays, and we know that they carry a lot of energy, that they can do a lot of damage to human tissue. And so it is the frequency of the waves that affect the energy and not how bright or the intensity of the wave. And the equation for that energy is H times F. F being the frequency of the wave, and the H there is a constant called Planck's constant, and that's 6.63 times 10 to the negative 34 joule seconds. And the photoelectric effect then suggested the particle nature of light. And how was that? Well, it was saying if we collide a surface with something, we can eject a particle out, then light must behave as if it's some sort of a particle. And so that particle is described as tiny little packets of light, tiny little packets of energy, which is called quanta. And you might be familiar with quanta from quantum mechanics, right? So we've seen the energy of our waves, or which would be the Planck's constant times the frequency. We can take any frequency for any of the waves that we have, multiply that by the constant, and we can get that energy in joules. Waves with higher frequencies have a greater amount of energies. And so now that we have this explanation for light having certain particle or quanta of energy that can knock another particle out of a surface, and we have an experiment that shows that light has certain characteristics that we know is characteristic of a wave, like constructive and destructive interference, we can describe light as having a dual nature, both a particle and wave-like characteristics. So let's talk a little bit about special relativity. Imagine you're driving down like a road, and you're in your car, you don't see yourself moving. So as far as you are, when you look out the window, you will see the trees, you will see the road, you'll see everything passing by your car. If you happen to be driving next to a car that's going at the same speed, and you look over, you can't see, you don't look like the car is really going as fast, because to you, you're both at the same speed, you're not moving. And that's where that relativity comes in. It's based on our understanding of how electromagnetic waves travel, and discusses observers in different reference frames and what happens to the light due to observers in different reference frames, as we'll see later in our discussion about how GPS systems work. So all motion is subject to the relative motion of the reference frame that we're in. And that's why it's very important in measurement to know the reference frame that we're in. If in our reference frame we're stationary, we can have a different measurement than if in our reference frame we're moving in our car. Another theory that talks or uses the fact, some of our understanding of the characteristics of light is in the general theory of relativity. So we have the special theory of relativity and we have the general theory of relativity. General theory of relativity states that there is a fourth dimension, and it's called space-time. And this is an interaction with mass and the space-time. Mass with space-time, showing the mass where to move in this continuum, in the space-time continuum. So one of the everyday uses we have of relativity is in our global positioning systems, or GPS. Currently around the Earth, we have about 31 satellites orbiting that are used for GPS. We need at least 4 satellites that's required to tell us our location. So again, we're going to watch a little video that's going to describe for us how the GPS system works and how the special theory of relativity and the general theory of relativity plays a role in determining what our location will be.
At over 20,000 kilometers above sea level is a constellation of satellites, each orbiting Earth every 11 hours and 58 minutes. These satellites are continuously beaming data down to us on Earth, which is in turn received by devices such as your phone or navigational units in your cars, allowing you to see where you are on the planet. There are a lot of misconceptions about how GPSs actually work, an example being that your phone and the GPS satellites are both talking to each other. So let's get down to it. How do GPSs work? GPS stands for Global Positioning System, which works through trilateration, not triangulation or multilateration, which is commonly misconceived. There are many different types of navigational satellite systems from countries across the world, but the most popular and commonly used system is Navstar, which is the USA system. There are, however, Russian, Indian, Chinese, and European equivalent systems, although the Indian and Chinese systems sit in a geosynchronous orbit above their countries, which means they are not worldwide systems. The Navstar system, which is simply referred to as GPS, is what we will be focusing more on, although most phones and devices tend to have the capabilities to use both GPS and GLONASS. GPS satellites are set up in such a way that from almost anywhere on the surface of Earth, you should have a direct line of sight of at least 4 GPS satellites. This is quite important on the basis that GPS point positioning requires at least 4 satellites to calculate 3 position coordinates and the clock deviation. As GPS units are receivers, there needs to be something sending some sort of signal to devices such as your phone to receive. Each GPS satellite broadcasts a navigational message towards Earth, which contains an extremely accurate timestamp, which is obtained through an atomic clock which is on board these satellites. And the satellites also broadcast their position at the time of broadcast, with all GPS signals broadcasting at 1.5752 gigahertz and 1.2276 gigahertz. These 2 bits of information allow you to work out your position on Earth. With these satellites all sending exceptionally accurate time down to Earth, your phone or GPS receiver can compare the difference of time between when the signal was sent to when it was received to work out the distance between you and the satellite. By multiplying this time difference with the speed of light, as the signal is sent at the speed of light, you can begin to get the distance away you are from that satellite. As these satellites are also sending whereabouts they are, you can begin to draw spheres around the satellites, with you being somewhere on the outer border of that sphere. As we introduce more GPS satellites into the mix, we begin to get closer to where we are. By calculating the time differences between these satellites, we move from having no idea where we are to being able to pinpoint where we are, typically down to 5 to 10 meters on average, with the potential error being around 15 meters. There are a lot of factors which escalate the potential error, but the most significant is due to the ionosphere, a part of the upper atmosphere extending from 60 kilometers to 2,000 kilometers, where free electrons occur frequently enough to have an appreciable influence on the proportion of electromagnetic waves passing through this layer. This error is substantially smaller when satellites are directly overhead, compared to being larger the closer the satellites are to the horizon relative to you, as the path between you and the GPS satellites goes through more of the atmosphere compared to being directly overhead. Even things such as small variations in the atomic clocks found on board these satellites can cause major errors. A clock error of 1 nanosecond can translate to a 1 foot or 30 centimeter miscalculation. Then the theory of relativity kicks in, with the atomic clocks ticking ever so slightly slower than clocks which are stationary on the ground, which translates into a 7 microsecond a day delay. General relativity then also kicks in, with the effect of the gravitational frequency shift being far greater than the 7 microsecond per day delay due to the velocity relative to Earth. As the theory states that a clock which is closer to a massive object will be slower than a clock further away, the atomic clocks on board the GPSs are faster by about 45.9 microseconds per day. Combining the 7 microsecond a day delay due to the satellite's velocity relative to Earth and the GPS is being further away from Earth, this adds up to a 38 microsecond delay, which if left uncorrected would translate through to a 10 kilometer a day pseudo-range error, rendering GPSs invalid from the get-go if this was not to be taken into consideration. This is compensated by the GPS's clock's frequencies being slightly slowed down from 10.23 MHz to 10.229999999543 MHz to cancel out the effects of relativity. So next time you turn on your GPS on your phone or other device, you should now realize just how much physics and maths is going in towards you finding your own location. Thank you for watching. Be sure to subscribe.
All right, so hope that sort of helped you understand a little bit about the application of special relativity and general relativity as it is applied to our GPS or global positioning system. Thank you, and that is the end of chapter 7.